Okay. So today in this session we'll discuss about resistive load inverter. Okay. So what is the impact of this resistive load on the inverter circuit? So that we are going to study in this session. So as you can see, this is a typical the resistive load inverter circuit. So this is the you can say this is most important, and we have a supply voltage VDD, and along with our this resistance VR is connected here. We're taking the V out here, and this is VDS, and this is our drain current which is going here. This is our input voltage, that is here. This is our gate, and this is our source. So this is our VGS, as you know. So this is our input voltage VGS. Okay, and this is our supply voltage VDD. So like this. Okay, so the IR, which is the resistance, the current which is going through this load resistance R, is nothing but W dot VSAT dot COS. So W is the channel width, saturation voltage, C is the offset capacitance, V is the input voltage, VT is the threshold voltage, V is the input voltage, and this ECL, L is the channel length. So that constitutes our current IR. Okay. So the basic structure of the resistive load inverter circuit that we can see here in this figure. Okay. So as in the general inverter circuit already examined, that an enhancement type NMOS transistor acts as a driver device. Okay, that we have already studied in our previous class. So basically the load consists of the simple linear resistors RL that we have seen here, RL, and the power supply voltage of the circuit is VDD. Now, since the following analysis is concentrated on the static behavior of the circuit, the output load capacitance is not shown in this figure. Okay, so here we are not taking into consideration the output capacitance value. Now, the drain current ID of the driver MOSFET is equal to the load current IR. Okay, so this load current ID IL that we call it is equal to the IR, the load resistance current IR. We can say it. Okay, fine. So that ID, the drain current ideal driver MOSFET is equal to load current IR in DC steady state operation. Okay. Now, in these cases, our channel length modulation coefficient we take into consideration, and that is considered to be zero. So, channel length modulation coefficient is zero in these cases. Okay. Now, if you can see here that the source and the substrate terminal are connected to the actually ground. Okay, you can see here. This is the source and the substrate is all connected to the ground here. Okay, when you take into consideration of the resistive load inverter circuit. Okay. So that makes to that VSB is equal to 0. The substrate to base this is actually VSB is equal to actually 0 in these cases. So consequently, the threshold voltage of the driver transistor is equal to our VT0. So threshold voltage is equal to is nothing but is equal to a threshold voltage. Now, for input voltage smaller than the threshold voltage, the transistor is in actually cutoff region. Okay, so that only you know that if the input voltage is less than the threshold voltage, the transistor is cut off. It does not conduct any drain current. Now, since the voltage drop across the load resistance is equal to 0, the output voltage must be equal to the power supply voltage. So that is equal to this supply voltage VDD. Okay. Now, as the input voltage is increased beyond VT0, the threshold voltage, the driver transistor starts conducting non-zero drain current. Okay. So in these cases, what about the IR that we call it, the current going through this IR is given by this expression. So that already we discussed. IR is equal to W V sat dot Cox V in minus VT0 whole square V in minus VT0 is here. Where N is the channel length, it is VT0 threshold voltage, C of the offset capacitance, and so is the channel width. Okay. Now, this is very important. So, when we take into consideration the operation region of the driver transistor in the resistive load inverter. Okay. So, if we take into this consideration, This what is the operating region we need to take into consideration. So that determines what operating mode the our transistor is operating. So remember this one, if the input voltage is less than the threshold voltage, so that is operating in the cutoff region. Okay. But let's say our input voltage is greater than equal to threshold voltage, but less than equal to output voltage plus our threshold voltage, so that is operating in the saturation region. Okay. Now, if the input voltage is greater than the output voltage plus the threshold voltage, then that is operating in the linear region. So this actually some conditions we have to consider that based on the input voltage that we are seeing, so that determines the what is the operating mode of the driver transistor in the resistive load inverter. Okay. So I hope this is clear to everyone. So this we have to always think, okay, and also determine the condition accordingly. Now, with the increasing input voltage, the drain current of the driver also increases, and the output voltage starts to drop. Now, eventually, for input voltage larger than the V out plus VT0, the driver transistor enters a linear operation region. Okay, so this is very important. So, when the input voltage increases, the drain current of driver also increases, and the output voltage starts to drop. Now, in this cases, the input voltage, which is larger than the output voltage or threshold voltage, the driver transistor enters the linear operation region. Now, at larger input voltages, the transistor remains in the linear mode, and the output voltage continues to decrease. So, this is actually the current, the current which is going through the load resistance IR. Okay, taken into consideration of many terminating voltage like this input voltage, threshold voltage, output voltage, V out, and K is the constant that you know. Okay. Now this is the typical voltage transfer characteristic that is called it VTC, voltage transfer characteristic of resistive load inverter circuit, and so that is very important. Okay. Now this is some conditions we have to think and also determine accordingly. Okay, so this is our output high voltage. So as you know, the voltage transfer characteristics is drawn between output voltage with respect to input voltage. Okay, so this output voltage is actually our dependent variable, and this input voltage V is actually our independent variable. So output voltage is drawn with respect to the input voltages. Okay. So that means the y-axis, which is here, is the output voltage that is taken into consideration when we plot the graph with respect to the input voltage V. So this input voltage is actually a independent variable, which is in the x-axis, and this output voltage V is the our y-axis. So that we have already discussed regarding the voltage transfer characteristic that we call it VTC. Okay. As you can remember, we have studied about voltage transfer characteristics of ideal inverter, and another is that also the voltage transfer characteristics of realistic inverter. Okay. If you remember, one question was asked in the midterm exam. So we have to, so you have to draw like this accordingly. So this is the typical voltage transfer characteristics of resistive load inverter circuit, and there are certain points we have to take into consideration. So this is actually the output high voltage that equal to our supply voltage VDD. Okay, the VDD is supply voltage, as you know, and this is our actually VIL, that is input low voltage. Okay, and this is our input high voltage. And these two regions, as you know, the slope is equal to unity. Okay, so in these cases, our slope is equal to at this point. This point, our slope is actually unity. So dB out by dB in is actually unity. Here also, and in this case also, dB out by dB in is equal to unity. And so here it's about input high voltage, and VIN is input low voltage. Okay, and this is our threshold voltage. Okay, this is actually our threshold voltage VT0. Very good. And if you can see here, preliminary, it is actually in the parallel to x-axis, that is parallel to the input voltage. And after that, after the threshold voltage, sorry, So after the threshold voltage, the output voltage, the voltage transfer characteristic starts to decrease. Okay, so that means from up to threshold voltage, the curve is nearly parallel to the x-axis, that is parallel to the input voltage. But after that, it start to decrease. Okay, and here after that is finally again comes to the comes to the saturation. Okay, so this is the actually the voltage transfer characteristics of resistive load inverter. Now, we need to calculate that actually what is actually the output voltage and or output low voltage, and how we can calculate. Okay, so if you can see here that if you can note the output voltage V out is here. So this is nothing but V out is actually VDD supply voltage minus load resistance IL, and whatever the current is flowing through this load resistance, that is IR. Okay, so V out will be VDD minus RL into IR. Okay, so this is actually this is output voltage that we take. So this is actually find out. So when the input voltage, that is our input voltage is low, that is smaller than the threshold voltage of the driver MOSFET, then the driver transistor is actually cut off. So it is cut off region. So it is very obvious cases that when the input voltage is low, that is smaller than the threshold voltage of the driver MOSFET, the driver transistor is in cut off region. Since the drain current of the driver resistor is equal to the load current, so that means our the current which is flowing to the the load and the drain is equal to zero. So it follows that the output voltage in the inverter under this condition will be output voltage is equal to VDD. Okay. So this is the point where our output voltage is equal to our supply voltage VDD. Okay. Now, this is actually how we calculate the output voltage here, VOH. Now, if we can calculate VON, okay, output low voltage, and to calculate the output low voltage, VON, we assume that the input voltage is equal to VOH, that is input voltage, that VIN is the input voltage, and VOH is equal to output high voltage. So this input voltage is equal to output high voltage, that is nothing but is equal to supply voltage VDD. But as we know that if the saturation voltage VT sat is less than V out, then in this case the driver transistor operates in the linear region. Okay. So in this cases our load current, whatever the load current IR is equal to VDD minus V out divided by RL. Okay. So VDD is the supply voltage, V output voltage divided by load resistance RL. Now, using Kirchhoff's current law, KCL to the output node, that is our load current is equal to a drain current. So, in these cases, we can rewrite the equations like this. Okay, so VDD minus VOL divided by load resistance. So, this is K factor, right? K factor, as you know, is nothing but VOL C of W by L, right? We have already discussed and solved many numerical problems in this regard. Okay. So Kn divided by 2, 1 divided by 1 plus VON minus VC length. So this is our channel length actually, and your output low voltage 200 to VDD minus VT0. VDD is the supply voltage, and VT0 is the threshold voltage into VON output low voltage minus VON square. Okay, so VON is the output low voltage. So if we continue determining the VON, now to calculate the output low voltage, we assume that the input voltage is equal to VOH, that is VIN, that is input voltage is equal to VOH is equal to VDD. Okay. So since this VD sat, that the saturation voltage is greater than output voltage, then in this case the driver transistor operates in the linear region. Now this load resistance, this load current, the current which is going to load resistance is equal to VDD minus V out divided by load resistance RL. Okay. Now this Kirchhoff's current law which applied to the output of the node. So this load resistance is equal to drain current, and so as you see in the previous slide, so this the equation will be VDD minus VOL, that is output low voltage divided by load resistance, K divided by 2 into 1 divided by 1 plus VOL divided by ECLN within bracket 2 into VTT minus VT0 dot VOL square. So VOL actually output low voltage and VT0 is a threshold voltage and VTT is a supply voltage. Okay. In these cases, if you can see the second term of the denominator, what is the second term in the denominator? So this is actually the VOL divided by ECLN can be ignored for the analysis since VOL actually very small actually. So VOL is very small, so this term can be neglected. That is VOL divided by ECLN. Okay. Now VDD minus VOL divided by RL is equal to K divided by 2 into VDD minus VT0 VOL minus VOL square. Okay. If we can simplify this equation, then simplify equation is accurate for the first order and it's a simple quadratic in the VOL, which is solved to find the value of output low voltage without iteration. This VOL square minus 2 whole into VDD minus VT0 plus 1 divided by KNRN into VOL plus 2 divided by KRN into VDD is equal to 0. Okay. Now there are two possible solutions in this equation here, the above equation. We must choose that one that this is the physically correct. That is the value of output low voltage must be equal to 0 and VDD. Okay. Now it can be seen that the product KNRN is one of the important design parameters to determine the value of VOL. So finally, we'll get this VOL value. So this is actually our output low voltage. So supply voltage VDD minus threshold voltage plus 1 divided by KRN minus, if you take the square root, it will be VDD minus VT0 plus 1 divided by KRN whole square minus 2 VDD by KLRN. Okay. So this is actually, if you want to calculate VOL, so this is actually the calculation of the output low voltage. Now let's then we'll calculate what actually, if we calculate input low voltage, okay, VIL that we call it. If we calculate VIL, then how we can determine? So this input low voltage, actually VIL, which you call it, is very smaller than the two input voltage value. At which actually the slope of the voltage transfer curve become equal to -1. Okay, so this dB out by dB in is equal to -1. Now simple inspection that we can see in this figure. This, if you can see this figure, is the voltage transfer characteristics. So in these cases, our slope is actually unity. Okay, so dB out by dB out by dB in, and here also dB out by dB in is actually slope is equal to unity. So that point we have to take into consideration. So this voltage transfer characteristic of resistive load inverter circuit is very important. And here, if you can see in the insert, there are some design parameters are given. So like, and based upon this, the characteristics has been drawn. So here, the supply voltage VDD is taken 1.2 volt. Threshold voltage is given 0.58 volt, and this K constant for NMOS transistor, so that is 57 into 10 to the power minus 5 ampere per volt square. And this for calculate for the load resistance, we have taken 20 kilo. Now, based upon these parameters, which if we can design the circuit and we can find out the output voltage with respect to the input voltage characteristics, so that will come, the characteristics will show like this. Okay, so please remember this one, for the resistive load inverter circuit, how the voltage transfer characteristics will look like. So I hope this clears to everyone. Now, for the input voltage, we can calculate. So, by definition, this input low voltage is smaller of the two input voltage value. That means the slope of the voltage transfer characteristics becomes -1. That is dB out by dB in is equal to -1. A simple instruction shows that when the input is equal to VIN, that is equal to the input low voltage, the output voltage V out is only slightly smaller than the output high voltage, that is VOS. Okay. Now, consequently, this output voltage is greater than the difference between this input voltage minus threshold voltage, and the driver transistor operates in the saturation. Now we can start our analysis by writing KCL for the output. So if you can apply KCL to the output now, so it will come as VDD minus V out divided by RL equal to W into V sat into C ox multiplied by V in minus VT0 whole square divided by V in minus VT0 plus VCL. Okay, so this is actually important. And so the first term of the denominator, if you can see on the right hand side of the equation, can be ignored because VIN is slightly higher than the threshold voltage. Okay. Now hence this equation can be simplified to V sat is equal to EC by 2. Now we can put this value here. Now it will come as to be VDD minus V out divided by RL. So this is Kn by 2 into VI into VT0. Okay, this VT0 actually our threshold voltage. And K constant, as you remember, we have solved some problems. So that is mu and C ox WIN. Okay, so that actually for this NMOS transistor we can take into consideration. So this Kn is all about. Okay. Now, if you can satisfy this derivative condition, we can differentiate this both sides with respect to input voltage. Okay. Finally, if you can differentiate with respect to input voltage, so finally it comes out to be minus 1 by Rn dV out by dV in, which is equal to Kn Vi minus Vt0. Now, since actually this derivative of the output voltage result input voltage is equal to minus of this input voltage, we can substitute this dB out by dB in is equal to minus 1. Okay, so this dB out by dB in, which is the slope we call it. So, because as you know, the output in the output y-axis, we have the output voltage and the x-axis input voltage. So, if we take the slope, so this is the slope here. So here, as you know, dV out by dV in, here also dV out by dV in is equal to minus 1. So we can put this value. So if you dV out by dV in is equal to minus 1, so put it here. You can put it here. So it comes to Kn Vi by Vt0. So if you can solve this equation, finally we got this input low voltage is equal to threshold voltage Vt0 plus 1 divided by Kn Rn. Okay, when Rn is the load resistance. Okay. Now, this value of the output voltage when the input voltage is equal to VIL, input low voltage, can be found by this equation. So, V out like a V in low input low voltage is equal to VT supply voltage minus W. W is the channel width, C of is the oxide capacitance, 1 divided by KLRL, L is the channel length in RL. So finally, it comes to be VDD minus 1 by 2 K RL. Okay. So please remember, when we calculate the input low voltage, we have to calculate like this. The calculation of input high voltage also will be the same thing. Okay. So if you can see the equation, this input high voltage is larger of the two voltage points. At least the slope is equal to minus 1. Okay. So when the input voltage is equal to input high voltage, the output voltage is only slightly larger than the output low voltage VOL. Okay. So this, if you can, the inequality is satisfied here. So V out output output voltage is less than the difference between input and threshold voltage. And the driver transistor operates in the linear region, and the KCL equation of the output node is actually this value. So this is the equation. If you can put the output, so VDD minus V out by load resistance, which is equal to Kn by 2, 1 divided by 1 plus V out by EC line, 2 into VIN minus threshold voltage into V out minus V out square. Okay. Similarly, here this V out divided by ECLN can be ignored because V out is very small. The V out very small, that output voltage is small. So this term V out by ECLN can be ignored. So if you can rearrange this equation, it comes out to be VDD minus V out divided by load resistance Kn divided by 2. Or in the bracket, if it can see the 2 into Vi minus Vt0 into V out minus V out square. Now, if we can differentiate this equation with respect to input voltage, okay. So if we can, whatever the equations we get it here, if we can differentiate both sides with the input voltage, so it comes out to be minus 1 by RL. When RL is the load resistance, dV out by dV in, K by 2, N by 2, what we call it, 2 multiplied by difference of input voltage and threshold voltage, dV out by dV in plus 2 dV out minus 2V out dB out by dB. Okay. Now, as you can see here, dB out by dB in, we have to put this value minus 1. Okay. To put this value minus 1. So, if we can put this minus 1 in this equation, then we can find out uh, this this equation. Okay. Because as you know, since the slope of the voltage transfer characteristics is equal to minus 1, also this input voltage is equal to input high voltage. So if you can put this value, that means dB out by dB in is equal to minus 1. Also at V input voltage, input high voltage, then finally you get this equation. Now if you can solve this equation above, then finally we get input high voltage is equal to threshold voltage VT0 plus 2V out minus 1 divided by K and RL. So again, if you can rearrange this equation, this input high voltage, it comes to be threshold voltage plus 2 V out plus minus 1 Kn into RL. Now, to determine the unknown variables, we substitute this equation actually into here. Okay, so we can put this equation, but whatever we get it here, we put it here. This is equation, the 5.27 equation, what you call it, we put it here. So the positive value of the second order equations gives the output voltage V out, which is actually input voltage is equal to input high voltage. So this comes to be root over 2 by 3 into VDD divided by KRL. So finally, we get this input high voltage is equal to threshold voltage plus square root of 8 by 3 VDD into KNRL minus 1 by ARL. Okay, this is actually our input high voltage. So this four critical voltage, as I already discussed in my previous classes: output low voltage VOL, output high voltage VOH, input low voltage VIL, and input high voltage VIH, can be used to determine the noise margins. Okay, this noise margins LMN, noise margin low level, and noise margin high level LMH for the resistive load inverter circuit. Now, in addition to these voltage points, which characterize the static input-output behavior, the inverter threshold voltage can also be calculated in that way. Okay. So this is actually the voltage transfer characteristics of the resistive load inverter for different parameter value for K and RL. So this is we take for this one when we design this resistive load inverter, we take into consideration some parameters value. So here, what are the parameters we have taken? The supply voltage VDD is taken 1.2 volt. Okay, threshold voltage is taken 0.48 volt, and for different the product of K and RL value, that like here 6 volt inverse, here it is 9 volt inverse, 12 volt inverse. The output voltage is plotted with respect to the input voltage. Okay. So this is the actually voltage transfer characteristics of the resistive load inverter for different parameters value of K and RL. Okay. So if in the exam it will the question will be asked that draw the voltage transfer characteristics for different parameters value for KRN, then you could draw like this. Okay. So this is all about for today's session.